Bevel gears are used in everything from electric hand drills to helicopters to differential drives in common automobiles. Bevel gears are commonly mounted on shafts that are 90 degrees apart and have conical shapes. This project focuses on stress concentrations at the root of teeth in two beveled gears. To create the part, we used a gearbox toolkit in Autodesk Inventor and imported the geometry into NX for further modifications. In NX, we added center holes to mount on the virtual shafts, and we added radius edge blends between two of the teeth to change the stress concentrations. These two different part files, one with square teeth and one with rounded teeth, were then imported into ANSYS for stress analysis. A mesh was first created using default element types and sizing. To increase computational efficiency, the mesh was only refined on the two teeth that make contact. Further refinement was applied at the root of the teeth, as this is where stress concentrations will be compared. Frictionless supports were added to the front and back faces of both gears, as well as to the center shafts. Additionally, unit moment loads were applied to the center axes of both gears. Equivalent stress was then solved for this system. In both sets of gears, equivalent stress is very small in most of the part. Stress distributions are only visible in the two teeth making contact. The gear with rounded teeth shows a gradual change in stress across the tooth. The square tooth gear, however, has very sharp changes in stress near the roots of the teeth. While stress distributions in the middle of the teeth may seem different, this is only due to the stress concentration in the square tooth gear skewing the color bar. Stress distributions near the point of contact between the teeth is likely to be inaccurate. This is because a bonded contact had to be used in order for ANSYS to converge on the solution. However, the total force transfer is the same, and the stress distributions near the root of the teeth are likely to be accurate. A path geometry was used to better assess stress at the roots of the loaded teeth. For the rounded gear, stress was approximately 1.25 megapascals for most of the tooth, rising smoothly to a maximum of 2 at the outer edge. The square tooth, however, averaged approximately 5 megapascals, with a sharp maximum of 8 at the inside edge. The stress plot is extremely jagged due to the sharp corner causing a stress concentration. Finite elements cannot accurately model such concentrations, yielding the noisy results. This study highlights two major points: the importance of accounting for and avoiding stress concentrations when designing a part, and the inability of FEA models to represent such stress concentrations.